and magnetic field is in downward direction. So force will be out of the paper, right?
Yeah.
So it means PVWS. So this side becomes the negative one, right?
Right, right.
So this is the first part. And in the second part, explain why electrons do not continuously accumulate on the face you have shaded.
Because like the charges will repel each other when they're like the same charge. Like
Okay.
they're gonna have to move.
So we know that when both forces becomes equal and opposite to each other, they cancel out each other. So definitely after that, electrons moves in a straight line. They will not further accumulate or not deposit on that same phase, right? So initially accumulate as their magnetic force, because initially we are using left hand rule, so there is only magnetic force acting, and then the accumulating electrons will make phase PSVW negative. Therefore, this starts to repel more incoming electrons, because this phase becomes negative and it will continuously becomes more and more negative, and when it becomes very like highly magnet negative charge side, so it starts to repel the incoming electrons, right? Because it already becomes so much strong negative side, so it further repels the new incoming electrons. And definitely at some point electrons starts to move in a straight line.
And it would
Pausing.
stop, right? Like when the quantity is near like the same like magnitude, you could say, as the magnetic force.
Correct. So it will cause the electric force to equal
Make the light.
the magnetic force.
Azan is happening for me, so can I like close
Okay.
my microphone?
So these are the first initial two parts related
Okay.
to the Hall probe, and the rest of the part of the Hall probe is now the Hall voltage VH develops across the foil in B is given by this expression, just like we drive.
Yes.
So where
So
I
when they said meaning of
Mhm.
the quantity and the number density of electrons.
Yes. So they are asking about the meaning of the quantity n. So we already know about this is the number density of electron. And second part, using the letter on figure 9.1, identify the distance t. So again, we need to check the diagram. and identify the distance t, like the thickness basically.
Okay.
So we can say that this side PV, right, or SW or QT, right? So these sides represents the T.
Okay. The thickness, basically.
So in answer, we can say PV side, SW side, or QT side. So this is the final answer for the second part. Okay, next, suggest why in practice hall props are usually made using a semiconductor material rather than a metal.
Um, is this in the book or do I have to like suggest a reason from like
Basically, always like we use hall prop made up of the semiconductor. So why this is happening? Because in metals we have high like number density of electron, right? So we can say metals have high number density of electron, and according to the formula, Hall voltage is inversely proportional to the value of n, right? So let's suppose if we use metal, so the value of n increases and the Hall voltage decreases. So we will get a small voltage, like a small Hall voltage if we are using metal. So in using the metal will increase the number density of electron, and that will decrease the Hall voltage. Okay. So that's why we use semiconductors, because in semiconductors we have less number of density of electrons as compared to the metal. So we can easily get the maximum Hall voltage, right?
right. Okay.
So the Hall voltage produced too small to measure. So that's why we are using semiconductors.
Because the number density is less, so the voltage would be greater, so you could actually measure it.
Yes. So we can measure it easily. So you observe this is like from 2021, because in old papers we have old syllabus. So that's why we consider the new one first. And if we consider now some old questions, so we have another in 2018. So this is another question related to the same hall prop topic. And in this diagram,
Okay.
yes, again we have a thin slice of conducting material, has its faces PQRS and VWXY, normal to a uniform magnetic field, flux density P. In previous question, you observe electrons' directions are from left to right. This time we have right to left. So electron entered the slice at right angle to the face SRXY. A potential difference, the Hall voltage VH is developed between two faces of the slices. Use letter from figure 9.1 to name the two forces between which the Hall voltage is developed. So between which two faces the Hall voltage developed in this diagram.
It's gonna be between okay, wait, let me do the thing. Would it be like the PSVY would be like one of them?
Okay. PSVY. Okay.
Am I right?
Correct.
Okay. And then like logically it should be the one opposites to it.
Opposite
So like
QWRX.
RX.
Correct. So definitely, again, if we use the left hand rule, so by using the left hand rule, what happens? That magnetic field is acting in downward direction and current moves from like right to left, the conventional current. So by using the left hand rule, force will be like into the paper. Correct?
Correct.
So this side becomes positive one and this becomes negative, and electrons starts to deflect in this direction. Okay, so we identified the directions or the faces in which the electrons deposits. And next part is the state and explain which of the two faces named in A1 is the more positive. So we already marked that PVSY becomes positive.
Yeah.
So electrons accumulate on the other side. So it becomes PVSY more positive. So they are asking state and explain. So we also need to explain. So using Fleming's left
Left
hand rule.
hand rule.
Yes.
We decipher that.
Must be more positive. Again, you can see they are asking the same type of question, the name of the symbols. So in B part 1, use the letter in figure 9.1 to identify the distance T. So which phase represents T?
From like left to right. So like SYRX and then PVQW.
Correct. Second part is same. So you can see we got exactly the same repeated type question because we have no calculation required in this question. So definitely we got
Awesome.
almost same type of question.
Yeah, it's like more conceptual.
Yes. Because if you identify wrong side, for example, in whole prop, so definitely whole question will be depends upon your diagram and identifications in the diagram. So if you identify wrong side, so definitely we will be getting like 0 mark in the that question because we select wrong side. In third part, state and explain the effect, if any, on the polarity of hole voltage when negative charge carrier or electrons are replaced with positive charge carriers moving in the same direction towards the slice. So now we need to replace electrons with the protons. It means positive side is over here now, and electrons are on the other side. So definitely there will be a change or no change. What do you think? If we change the direction of current?
I don't think there's gonna be like any change.
Yes, but only there is like change of direction. Like now negative will be on PSVY side. So direction of magnetic field is still remains the same and we got same value of T. So there will be no change.
But only directional like switch.
Yes. As positive charge carriers will still deflect to base PSVY, right? So these are the ideas from the Hall prop. Okay. And one more thing, last time, like before this Hall prop topic, we discussed about this idea of charge in a uniform magnetic field, right? Charge in a magnetic field. And we use values to find out the quantities related to charge in a magnetic field. But we have another idea related to the velocity selector. Discuss about the
Okay, second.
we discuss about velocity selector and we also find out the value related to the velocity selector. But we have another idea that is called like charge to mass ratio or fine
Right.
tube experiment. So that is the topic that is still we need to complete. So basically in fine tube experiment,
In this, can you actually like observe the electrons and everything moving?
yes. And it is also called like charge to mass ratio. In syllabus, it is mentioned like E over M, charge to mass ratio. So in other words, we can also say it is called like fine tube experiment.
Okay.
Yes. Because this method is used to find out charge to mass ratio of an electron. So now let's suppose in this experiment we have a tungsten material over here.
Is tungsten a semiconductor or like a conductor?
It is a conductor like in old orange bulbs, we use that tungsten material and you know that emit out very high amount of thermal energy, right?
Okay.
So when we
Yes.
provide a specific amount of energy to the metal, so electron starts to emit from there.
The photoelectric effect, right?
Yes. So this side is positive and this one is negative. So electrons are emitting out from here, and now they are accelerating in forward direction. And then again it travels through the electric field. So we can use the same plates, positive and negative. And magnetic field moves in the downward direction from positive to negative. And the magnetic field is into the paper like this. And further, it travels in forward direction still. And then it starts to again make that circular path because of magnetic field. Because in last we are using only magnetic field like this.
So because the magnetic field is the reason why it turns around again.
Yes. So just like the last topic we discussed, this is like we can say another method to find out the quantities, just like we discussed in the previous topic before Hall probe. This
Yeah,
one.
yeah, the one when it also turns
Yes.
around.
So basically, in this fine tube experiment, we combine electric field and magnetic field to get the same scenario of circular motion of the electron in a magnetic field.
Right.
And further, if we talk about the quantities, so work done is equals to WQ, or we know that it is moving. So during the motion, we have kinetic energy, and kinetic energy is equals to half mv square, half mv square, or v is equals to under root 2 times vq over m, right? And we also discussed that v is equals to e over b. And when we are getting this circular motion, so in this circular motion, there are two methods to measure this radius r. So let's suppose if you want to measure this radius r, so there are two methods. Either we can measure by taking the picture of this specific circular motion, right? Or the other method is to measure with the help of a traveling microscope. Okay. So traveling microscope is like laboratory apparatus that we use to observe the moving things. just like this. Or the other method is to take picture and find out the radius from that specific picture. Okay.
How
So
reliable is the method?
basically we know that we are providing uniform magnetic field. Okay. So it will give you a uniform circular motion, right? Because magnetic field is not changing, so definitely it will not affect anything.
Yeah.
It will like make change once and that will remains the same. So practically, like in laboratory process right now, we are not performing this experiment in A levels, but like at university level we have this type of experiment to perform because we have advanced apparatus and machineries over there. So let's suppose if you got chance to perform that experiment, so now we are using advanced technology, so we can easily take pictures of that whole experiment. Just like if we take example of x-ray, so in x-ray we got a result on the photographic plate, so that is the example of like taking a picture. That is a picture, black and white, in simple words, right? That photographic plate. So in the same way, when we observe the charges moving in a circular path, so we can take picture over there like the traces of the electrons or the traces of the charges. Or the other method is we can use the traveling microscope to find out the radius. So let's suppose we measure radius. Like if you use normal microscope, so normal microscope helps you to like zoom in, zoom out, or like change species to measure or like to take observation. But in traveling microscope, you have two axes given, vertical and horizontal. So it's your choice. You can make that microscope move in vertical direction, or you can also move that microscope in horizontal direction. Because this is a circular motion, so we have both axes. So you can use traveling microscope to exactly identify the direction of that charge from the center. Okay.
Okay.
Like in our university, we use this traveling microscope to find out that surface tension in the liquid. So we measure upper meniscus and lower meniscus with the help of this traveling microscope and then substitute the values in the formula to find out the concept of the surface tension. So in this way, we use traveling microscope in this different experiment where you have to measure like vertical and horizontal both directions or dimensions. Again, we have a
Okay.
same idea. The centripetal force is equals to the force due to magnetic field, and it will be equals to mv square over r is equals to, so v and v cancel out one power, and now it will be equals to charge to mass ratio q over m is equals to this equation, right?
Right.
So this is the concept of charge to mass ratio or the equation for charge to mass ratio.